The story of the far future begins with space itself on the larger scales where the universe continues to expand and reshape what can be seen from any single point. On these scales, galaxies are not fixed landmarks, but distant systems carried by the stretching of space. This expansion does not move galaxies through space in a simple way, but instead increases the distance between regions of space over time. Light traveling across these vast distances slowly loses the ability to reach every observer forever, because the space it moves through is also growing. As time progresses, more distant regions pass beyond a boundary where their light can ever arrive, even in principle, and this boundary is described as the cosmic horizon. The cosmic horizon is not a physical wall, but a limit defined by the age of the universe and the rate of expansion. It marks the edge of what can be observed and what can influence a given region. As expansion continues, this horizon shifts and more distant galaxies slip beyond it. From any single gravitationally bound region, the visible universe gradually becomes smaller in terms of reachable information. Galaxies that were once visible remain as faint memories of light that stretches and weakens until it can no longer be detected. Over extremely long timescales, the sky becomes less populated with visible structures, not because they vanish instantly, but because their light can no longer bridge the growing separation of space. The expansion is driven by the large-scale properties of space-time itself. Observations of distant galaxies show that they are moving away in proportion to their distance, a pattern known as cosmic expansion. This behavior becomes more dominant over vast distances where gravity is too weak to hold structures together. In local regions, gravity resists this trend, keeping systems like galaxies and galaxy clusters bound. However, beyond these bound regions, expansion dominates, and space continues to stretch without being constrained. As the universe expands, the distribution of matter becomes increasingly separated. Galaxy clusters that are not gravitationally bound drift apart over billions of years. The light emitted from distant galaxies is stretched into longer wavelengths, becoming less energetic and harder to detect. This process, called redshift, reflects the stretching of space itself, rather than motion through space in the usual sense. Over immense timescales, redshift becomes so extreme that even visible light shifts into wavelengths that are no longer easily detectable by conventional means. Within any single gravitationally stable region, the expansion of space is not noticeable at small scales. Atoms, planets, stars, and galaxies remain stable, because their internal forces are far stronger than the effect of expansion at short distances. Yet, on the largest scales, the cumulative effect defines the structure of the cosmos. It creates a separation between regions that can interact and regions that can no longer exchange information. This separation grows slowly but steadily, shaping the long-term accessibility of the universe. The observable universe is defined by what light has had time to reach an observer since the beginning of cosmic expansion. As time continues, this observable region does not simply remain static. It evolves because some regions move out of reach while others remain accessible. The visible structure becomes increasingly concentrated around local gravitational systems. Distant galaxies, once part of a rich cosmic panorama, fade into irrelevance, not by destruction, but by disconnection. On these scales, the universe appears increasingly isolated. Each gravitationally bound system becomes its own island, surrounded by expanding space that carries other systems away. Communication across these islands becomes impossible, as the distance grows faster than light can traverse. The structure of the cosmos becomes defined not by uniform distribution, but by separation into independent regions. Each region continues to evolve according to its own internal dynamics, while the larger cosmic web stretches beyond interaction. The energy density of space also changes as expansion proceeds. Radiation that fills space becomes more diluted, its wavelength increasing as the fabric of space expands. This leads to a gradual cooling effect on the large-scale background environment. Even the faint microwave background radiation that fills the universe today becomes increasingly stretched and weakened over time, blending into an even colder and less energetic background state. Despite this vast expansion, the laws of physics remain consistent. Gravity still binds matter locally, and electromagnetic forces continue to govern atomic and molecular structure. What changes is not the nature of these forces, but the distances over which they can dominate. The expansion of space determines which structures remain connected and which become separated beyond interaction. Over extremely long durations, the universe becomes dominated by isolated regions of matter, embedded in a vast expanding void. These regions retain their internal structure, but their connection to the wider cosmos diminishes. The cosmic horizon continues to define the limit of observable influence, gradually enclosing each region within its own accessible domain. The large-scale universe becomes less a connected whole and more a collection of separate, unreachable systems drifting in an expanding framework of space. In this outermost layer of cosmic existence, structure is defined not by formation but by separation. Space itself becomes the dominant influence determining what can remain part of any observable reality. As expansion continues without interruption, the visible universe from any one location steadily reduces to its most local structures, while everything beyond fades into a silent, unreachable distance, shaped entirely by the stretching of space. Within the evolving universe, the next scale inward is defined by gravitationally bound systems that resist the outward pull of expansion. These systems include galaxy groups and galaxy clusters, where gravity is strong enough to hold matter together despite the stretching of space between distant regions. On these scales, the universe does not expand in a way that tears structures apart. Instead, it allows them to remain stable, forming long-lived islands of matter surrounded by increasingly empty space. These gravitational regions become the fundamental units of cosmic persistence over vast timescales. A galaxy group forms when a small number of galaxies become bound by their mutual gravitational attraction. Over time, these systems settle into stable orbits around a shared center of mass. Within such groups, galaxies interact through slow gravitational tugs, exchanging energy and occasionally merging. The structure is dynamic but remains coherent because the total gravitational energy is sufficient to keep the system intact. Even as space expands on larger scales, these bound systems remain unaffected in their internal structure. Galaxy clusters represent larger and more massive collections of galaxies. They contain hundreds or even thousands of galaxies held together by gravity, along with vast amounts of hot gas and dark matter that contribute to the overall mass. The gas within clusters is heated to extremely high temperatures through gravitational compression and collisions, producing faint X-ray emissions that reveal the presence of these enormous structures. Despite their scale, these clusters are still gravitationally bound and do not expand apart internally. Dark matter plays a central role in maintaining the stability of galaxy groups and clusters. It is a form of matter that does not emit or absorb light but exerts gravitational influence. Observations of galaxy motion within clusters show that visible matter alone is not sufficient to explain their stability. The presence of additional unseen mass is inferred from these motions, and this mass helps hold the structure together over billions of years. Without it, many clusters would not remain bound. Inside these systems, galaxies orbit in complex patterns shaped by gravitational interactions. Some galaxies pass close to one another, distorting their shapes through tidal forces that stretch and compress their stellar distributions. These interactions can trigger bursts of star formation by compressing clouds of gas, temporarily increasing the rate at which new stars are born. Over long periods, repeated interactions gradually transform galaxy shapes, turning spiral structures into more elliptical forms. Despite these internal dynamics, galaxy groups and clusters are increasingly isolated from one another as cosmic expansion continues. The space between clusters grows over time, and distant clusters recede beyond the ability to exchange light or matter. Each cluster becomes a self-contained environment, evolving independently from others. This isolation marks a transition in cosmic structure, where large-scale connectivity gives way to separated gravitational systems. Within a single cluster, time continues to shape structure through slow gravitational evolution. Galaxies gradually lose gas as it is heated and stripped away during interactions and motion through intracluster medium. This gas does not easily cool back into star-forming material, leading to a gradual decline in new star formation. As a result, clusters evolve toward populations dominated by older stars and long-lived remnants. The intracluster medium itself remains a significant component of these systems. It consists of extremely hot diffuse gas that fills the space between galaxies within the cluster. This gas is held in place by the cluster's gravitational field and continues to emit faint radiation as it cools slowly over time. Although extremely sparse compared to solid matter, its total mass can exceed that of all visible galaxies within the cluster combined. As clusters evolve, their internal structures stabilize further. Galaxies settle into long orbital paths, and interactions become less frequent as gas supplies diminish. The cluster becomes a more passive system, with less active star formation and fewer dramatic structural changes. Its evolution slows, governed primarily by gravitational dynamics rather than energetic processes. Eventually, galaxy clusters become the largest stable structures in the universe. They stand as gravitationally bound regions surrounded by an ever-expanding and increasingly empty cosmos. Beyond them lies space, where expansion dominates completely, preventing any new large-scale structures from forming between clusters. Each cluster thus represents a long-term cosmic island preserving matter in a bound state, while everything beyond recedes beyond reach. In this stage of cosmic evolution, structure is defined by persistence rather than creation. The universe outside clusters continues to expand and dilute, while within clusters gravity maintains coherence. These regions serve as the last large-scale environments where complex interactions between galaxies remain possible. Over immense timescales, they become the final visible architecture of matter before isolation becomes absolute on even smaller scales. Within the bound structure of a galaxy cluster, the next inward region of focus is the Milky Way's future evolution as it interacts with its nearest large companion galaxy. Gravity gradually dominates the motion of galaxies that are close enough to be bound within a shared local system. In this environment, the Milky Way and the Andromeda Galaxy move toward each other under mutual gravitational attraction. Their paths are shaped not by sudden motion, but by a slow, continuous acceleration that unfolds over billions of years. The space between them shrinks steadily as their combined gravitational field overcomes the expansion of space within this local region. As the two galaxies approach their outer regions, begin to interact first. These outer regions contain sparse distributions of stars, globular clusters, and diffuse gas. The interactions are gentle at first, driven by long-range gravitational forces that slightly distort stellar orbits. Individual stars rarely collide because the distances between them are extremely large compared to their sizes. Instead, the primary effect is the reshaping of the galaxy's overall structures as tidal forces stretch and shift their outer halos. The Milky Way and Andromeda are both spiral galaxies, but their spiral structures are not rigid. They are patterns formed by waves of density moving through rotating disks of stars and gas. As gravitational interaction increases, these patterns become disrupted. Spiral arms become less distinct, and the ordered rotation of each galaxy begins to lose its original symmetry. Stars continue to orbit the galactic centers, but their paths become increasingly complex as the gravitational fields of both galaxies overlap. Gas clouds within each galaxy respond more strongly to these interactions than stars do. Gas is more easily compressed and disturbed, and it can lose energy through radiation, allowing it to collapse into denser regions. As the galaxies draw closer, these gas clouds are compressed in certain regions, triggering bursts of star formation. These bursts are temporary, fueled by the redistribution of material rather than a continuous supply of new gas. Over time, the available gas is gradually consumed or expelled, reducing the potential for future star formation. Dark matter halos surrounding both galaxies play a crucial role in guiding the merger process. These halos extend far beyond the visible edges of the galaxies and contain most of their mass. As the halos overlap, they interact gravitationally, creating a shared potential well that eventually binds the two systems into a single structure. The visible components of the galaxies respond to this combined gravitational field, gradually settling into new orbital configurations. As the merger progresses, the structure of both galaxies becomes increasingly distorted. Stellar streams form as groups of stars are pulled into elongated arcs by tidal forces. These streams trace the gravitational history of the interaction, revealing how matter is redistributed over time. Some stars are ejected into extended orbits, forming diffuse halos around the merging system. Others remain in more stable orbits closer to the central regions. The central regions of both galaxies become increasingly active during this process. Gas is funneled inward toward the galactic centers, where it accumulates in dense regions. This inward flow of material can feed central supermassive black holes, increasing their activity. As matter falls toward these compact objects, it releases energy in the form of radiation, heating the surrounding gas and influencing the environment of the galactic core. This phase is energetic compared to the quieter outer regions, but it remains governed by gravitational dynamics rather than explosive processes. Over time, the distinct identities of the Milky Way and Andromeda fade. Their stars are redistributed into a single combined gravitational system. The final result of this long process is a larger, more diffuse elliptical galaxy, where the original spiral structures are no longer visible. The stellar population remains intact, but it is reorganized into a new equilibrium state shaped by the merger. Within this new structure, star formation gradually declines after the initial burst triggered by the collision. Most of the available gas has been consumed or heated to temperatures where it no longer collapses easily into new stars. The remaining stars continue to orbit within the merged system, forming a stable but aging population. The galaxy becomes dominated by long-lived stars and stellar remnants, marking a transition from an active formation phase to a more passive evolutionary stage. On these scales, the merger represents a local reorganization within a gravitationally bound region. It does not affect the expansion of the universe on larger scales, but it defines the internal evolution of one such island system. The resulting merged galaxy continues to exist as a single coherent structure within the cluster environment, gradually stabilizing into a long-term configuration shaped by the combined mass of its original components. Within the merged galactic structure formed from the long interaction of the Milky Way and Andromeda, the next inward region of cosmic evolution is defined by the gradual exhaustion of cold gas, the primary material required for new star formation. This gas exists in diffuse clouds of hydrogen and helium, spread throughout galaxies, forming the raw reservoir from which stars are born. Over long timescales, this reservoir is steadily depleted through repeated cycles of star formation, stellar feedback, and gravitational redistribution. The rate at which new stars form depends directly on the availability of this cold, dense material, and as it declines, the entire character of the galaxy changes. In the early stages of a galaxy's life, cold gas flows freely through spiral arms and dense molecular clouds. These regions are rich in hydrogen molecules that can collapse under gravity when sufficiently compressed. Star formation occurs when these clouds reach a critical density, allowing gravity to overcome internal pressure. In the merged galaxy, this process continues for a time, but the frequency of suitable conditions gradually decreases. The gas becomes more diffuse, heated by previous generations of stars and redistributed through galactic motion. Supernova explosions from massive stars play an important role in this transformation. When large stars reach the end of their lifetimes, they explode and release energy into their surroundings. This energy heats nearby gas, dispersing it, and preventing it from collapsing easily into new stars. Over repeated generations, this feedback process increases the temperature of the interstellar medium, making star formation less efficient. The combined effect of stellar winds and supernova slowly transforms cold, dense regions into warmer, more diffuse gas. As gas becomes more difficult to compress, the rate of new star formation declines. The galaxy enters a phase where existing stars continue to evolve, but fewer new ones are created to replace them. This shift marks a fundamental transition in the life of a galaxy, from a dynamic star-forming system to a more passive aging structure. The remaining gas becomes concentrated in isolated pockets, often located in regions where gravitational interactions or residual density fluctuations still allow limited collapse. Within these pockets, star formation continues at a reduced pace. New stars that form during this period tend to be smaller and longer-lived, as the conditions favour the creation of lower-mass objects. Massive star formation becomes increasingly rare because it requires dense, rapidly collapsing regions that are no longer common. As a result, this stellar population of the galaxy slowly shifts toward longer-lived, less luminous stars over time. The redistribution of gas is also influenced by the movement of stars and dark matter within the galaxy. As stars orbit through different regions, they gravitationally disturb nearby gas clouds, sometimes compressing them and occasionally dispersing them. These interactions create a complex and uneven pattern of star formation, with localized bursts occurring in otherwise declining environments. However, these bursts are insufficient to restore the overall rate of star formation to earlier levels. Over long periods, much of the remaining gas is either converted into stars or expelled from the galaxy. Outflows driven by energetic processes in the galactic center can push gas outward, removing it from regions where it might otherwise contribute to future star formation. This gradual loss of material contributes to the overall decline in the galaxy's ability to sustain new stellar generations. As the gas supply diminishes, the galaxy's appearance changes. Bright blue regions associated with young massive stars become less common. Instead, older, redder stars dominate the visible structure. The light emitted by the galaxy shifts toward longer wavelengths, reflecting the aging of its stellar population. The once prominent spiral features become less defined as new stars no longer trace the structure of gas-rich arms. The decline in star formation does not occur uniformly across the galaxy. Some regions retain pockets of activity longer than others, depending on local density variations and gravitational influences. Central regions where gas can be funneled inward may continue forming stars slightly longer than outer regions. However, even these areas eventually experience depletion as the overall gas reservoir diminishes, This stage of galactic evolution represents a transition from creation to persistence. Stars that already exist continue their life cycles, but the formation of new stars becomes increasingly rare. The galaxy becomes dominated by long-lived stellar populations and remnants of earlier generations. The structure remains gravitationally stable, but its internal energy sources slowly diminish. Over time, the decline in star formation leads to a quieter, more stable galactic environment. The dynamic processes that once defined the galaxy's structure give way to slow evolutionary changes governed primarily by the aging of stars. The galaxy remains intact, but its capacity to generate new luminous objects steadily fades as the cold gas reservoirs that once sustained it are gradually exhausted. Within the aging merge galaxy, the next inward region of cosmic evolution is defined by the dominance of red dwarf stars, the smallest and most long-lived class of hydrogen-fusing stars. As the reservoir of cold gas declines and new star formation slows, the stellar population becomes increasingly shaped by survival rather than renewal. Massive and short-lived stars have already completed their life cycles, leaving behind a population dominated by lower-mass stars that burn their fuel slowly and steadily over immense spans of time. Red dwarfs become the most common source of light and energy within the galaxy. Red dwarf stars form under conditions where gas clouds collapse, with relatively low mass producing stars that do not accumulate enough material to sustain high-pressure, high-temperature fusion environments. Their cores operate at lower temperatures compared to larger stars, allowing hydrogen fusion to proceed at a slow rate. This slow fusion process means that their energy output is modest but extremely long-lasting. While more massive stars exhaust their fuel quickly and evolve into compact remnants, red dwarfs remain stable on the main sequence for periods that extend far beyond the current age of the universe. In this stage of galactic evolution, red dwarfs dominate the visible stellar landscape. Their light is dim compared to larger stars, often emitting a faint red glow rather than bright white or blue light. Despite their low luminosity, their sheer abundance ensures that they remain the primary contributors to the galaxy's overall brightness. The galaxy, once filled with a wide variety of stellar types, gradually becomes a system where faint red points of light define the structure of the night sky. The internal structure of red dwarf stars is relatively simple compared to larger stars. Many of them are fully convective, meaning that energy and material circulate throughout the star rather than being confined to distinct layers. This convective mixing allows hydrogen fuel to be used efficiently throughout the star's interior, contributing to their long lifetimes. Because they burn fuel so slowly, they avoid the rapid evolutionary changes seen in more massive stars. As time progresses, red dwarfs remain on the main sequence for extraordinarily long periods. Their slow consumption of hydrogen means that they change very little over billions of years. While other types of stars evolve into giant supernovae or compact remnants, red dwarfs persist in a stable state. This stability makes them the most enduring sources of nuclear energy in the universe during this era of cosmic evolution. The surrounding galactic environment becomes increasingly quiet as new star formation declines. Without frequent formation of massive stars, the energetic processes that once shaped galaxies become less common. Supernova explosions, which once enriched the interstellar medium with heavy elements and redistributed gas, occur less frequently. The absence of these events leads to a more stable but less dynamic galactic environment. Planets that orbit red dwarf stars where they exist experience long-term stability in their stellar energy input. However, the broader galactic environment continues to evolve toward reduced complexity. The population of massive stars that once contributed to strong ultraviolet radiation and energetic feedback is no longer present. Instead, the energy output of the galaxy becomes more uniform and subdued, dominated by low-intensity radiation. As red dwarfs age, they continue to convert hydrogen into helium in their cores. Over extremely long timescales, their composition slowly shifts as helium accumulates. However, because their lifetimes exceed the current age of the universe by vast margins, many red dwarfs remain in relatively early stages of their evolutionary paths. They represent a long-lasting phase of stellar existence that outlives nearly all other stellar types. The dominance of red dwarfs also reflects the underlying mass distribution of stars formed throughout cosmic history. Most stars that have ever formed are low in mass, meaning that even as earlier generations of massive stars fade away, the galaxy naturally transitions into a red dwarf-dominated state. This shift is not abrupt but gradual, emerging as the higher mass population completes its life cycles. In this era, the galaxy becomes structurally simpler in terms of its luminous components. Bright and short-lived stellar phenomena become rare. The sky is filled with faint, stable points of red light, each representing a long-lived nuclear engine operating at a slow and steady pace. The energetic diversity of earlier cosmic epochs gives way to a more uniform and enduring stellar population, even as red dwarfs dominate the galaxy continues to evolve slowly. Gravitational interactions, residual gas dynamics, and the gradual aging of stellar populations all contribute to long-term change. However, the overall impression is one of stability. The galaxy is no longer a site of rapid transformation, but a slowly aging system defined by persistence and long lifetimes. Within the red dwarf-dominated galaxy, the next inward region of cosmic evolution is defined by the final generations of active stellar evolution, where the last significant waves of star formation gradually come to an end and the existing stellar population proceeds through its natural life cycles without meaningful replacement. At this stage, the galaxy no longer produces large numbers of new stars, and the few remaining episodes of starbirth become rare, isolated, and weak compared to earlier cosmic eras. The overall stellar population begins to reflect a completed history of formation, rather than an ongoing cycle. The stars that still exist at this stage are distributed across a wide range of masses, but the dominant presence remains low-mass, long-lived stars. Higher-mass stars, which once shaped the energetic structure of galaxies, have already completed their evolution. Their absence removes the most powerful sources of radiation, supernova enrichment, and dynamic feedback. What remains is a calmer stellar environment, where nuclear fusion continues primarily in low-energy, stable configurations. As the last meaningful reservoirs of cold gas are consumed or dispersed, star formation becomes increasingly sporadic. Dense molecular clouds, which once collapsed frequently under gravity to form new stars, are now rare and fragmented. The conditions required for sustained star formation, sufficient density, low temperature, and gravitational stability, occur only in isolated pockets. When they do occur, they produce small clusters of low-mass stars rather than large, diverse stellar populations. In these final star-forming regions, gravity still drives the collapse of gas, but the available material is limited. The resulting stars are typically small, cool, and long-lived, continuing the trend toward a galaxy dominated by slow-evolving objects. These newly formed stars do not significantly alter the overall structure of the galaxy, which is already defined by its long-lived stellar population. Instead, they represent the last faint continuation of a process that was once far more active. Meanwhile, existing stars continue their evolution along established pathways. Hydrogen fusion in their cores proceeds steadily, gradually converting lighter elements into helium. Over extremely long timescales, some stars begin to show subtle changes in composition and structure, But these changes unfold so slowly that they define an era rather than a moment. The galaxy becomes increasingly characterized by steady processes rather than dynamic transformation. The absence of massive stars has profound effects on the galactic environment. Without their strong stellar winds and explosive deaths, there is little new injection of heavy elements into the interstellar medium. Elements produced in earlier generations of stars remain distributed within existing stars, planets, and remnants, but the continuous recycling of material slows dramatically. The chemical evolution of the galaxy enters a long quiet phase. Supernova events, once common and highly influential, become exceedingly rare. These powerful explosions had previously played a central role in shaping galaxies by dispersing heavy elements and triggering new star formation. Their near absence marks the end of a major energetic cycle in galactic evolution. Without them, the interstellar medium becomes more stable, but also less dynamic and less enriched over time. The galaxy's structure during this phase becomes increasingly defined by its long-lived stellar population. Orbital motions of stars around the galactic center continue as before, but without the disruptive influence of new massive stars or frequent energetic feedback, these motions become more predictable and settled. The overall system approaches a form of dynamic equilibrium, where large-scale changes occur only over extremely long timescales. In this environment, stellar remnants from earlier generations become more prominent. White dwarfs, neutron stars, and black holes remain present, but they are now largely passive components of the galactic structure. They no longer form in large numbers as the processes that created the massive star evolution have largely ceased. Instead, they persist as long-lived endpoints of earlier stellar activity. The galaxy at this stage is no longer defined by formation but by continuation. Existing stars carry forward the last active nuclear processes, while the surrounding environment slowly stabilizes into a state with minimal new input. The energy output of the galaxy gradually declines as fewer new luminous sources appear, and the existing ones slowly age. Over vast periods, this transition leads to a galaxy that is still physically intact but increasingly static in its stellar composition. The final generations of stars represent the closing phase of active stellar creation, marking the end of a long sequence of processes that began with abundant gas, vigorous star formation, and frequent stellar death. What remains is a long-lived, slowly evolving system, moving toward a future defined not by creation, but by gradual fading. Within the galaxy that has entered its final generations of stellar activity, the next inward region of cosmic evolution is defined by the long-term cooling and fading of white dwarf stars. These objects are the dense remnants of low and intermediate mass stars that have exhausted their nuclear fuel and shed their outer layers. What remains is a compact core composed mostly of carbon and oxygen, supported against further collapse by electron degeneracy pressure, a quantum mechanical effect that arises when electrons are forced into extremely tight spaces and resist further compression. White dwarfs no longer produce energy through nuclear fusion. Instead, they shine only because they retain residual heat from their earlier life as active stars. This heat slowly radiates away into space over immense periods of time. At first, a newly formed white dwarf is extremely hot and luminous, but without a sustained energy source, it begins a gradual cooling process that continues for trillions of years. The rate of cooling is slow because the object is dense and efficient at retaining heat, but it is ultimately irreversible. As time progresses, white dwarfs shift from bright hot objects into dim cooling embers. Their surface temperatures steadily decrease, and their emitted light becomes weaker and redder. The visible radiation they produce gradually shifts out of the range easily detectable by ordinary observational methods. Even though they remain physically intact, their contribution to the galaxy's visible light diminishes steadily over time. The internal structure of a white dwarf remains stable during this cooling process. The material inside is in a highly compressed state, where atomic nuclei are packed closely together in a crystalline-like lattice as temperatures fall. This crystallization occurs because as the white dwarf cools, the ions within it settle into ordered structures, releasing latent heat in the process. This phase transition slows the cooling temporarily but does not stop it. Surrounding the white dwarf, any remaining planetary systems continue to orbit in long, stable paths. These systems may include remnants of planets, asteroids, and debris that survived the earlier phases of stellar evolution. Over time, gravitational interactions within these systems can lead to slow orbital changes, but the overall structure remains intact. Without strong radiation pressure or stellar winds, these systems become quiet and dark environments. White dwarfs are extremely stable objects in terms of their mass and structure. They do not collapse further under normal conditions because electron degeneracy pressure provides a powerful resistance to compression. However, their long-term fate is determined by the gradual loss of thermal energy. As they cool, they transition from luminous stellar remnants into faint, nearly invisible objects. In the broader galactic context, white dwarfs become increasingly dominant among stellar remnants as other types of stars complete their life cycles. Since most stars in the universe end their lives as white dwarfs, they accumulate in large numbers over time. Even as new star formation declines, the population of white dwarfs continues to grow for a period reflecting the delayed outcomes of earlier stellar generations. Eventually, as the galaxy continues to age, even the creation of new white dwarfs slows because fewer stars are reaching the end of their active lifetimes. The existing population becomes a static collection of cooling remnants. Each one follows a similar trajectory: slow, cooling, gradual fading, and eventual transition into a dark, inert object. Over extremely long timescales, white dwarfs move toward a state where they no longer emit significant visible or infrared radiation. They become difficult to detect against the background of space, effectively blending into the darkness of the galaxy. This stage represents a major shift in the observable structure of the universe, as one of its most common stellar remnants gradually disappears from view. Despite their fading luminosity, white dwarfs remain gravitationally significant. Their mass continues to influence nearby objects, and they remain stable components of the galaxy's structure. They do not evaporate or disappear during this stage. Instead, they persist as cold, dense remnants of earlier stellar evolution, quietly orbiting within the galaxy's gravitational framework. In this phase of cosmic time, the galaxy is no longer defined by active stellar processes, but by the remnants of past activity. White dwarfs serve as long-lasting traces of earlier generations of stars slowly cooling as the universe moves toward a quieter and more inert state. Their gradual fading marks another step in the transition from an active universe to one dominated by long-lived, slowly evolving remnants. Within the galaxy populated by cooling white dwarfs and fading stellar activity, the next inward region of cosmic evolution is defined by neutron star isolation, where the remnants of massive stars persist as extremely dense, compact objects drifting through an increasingly quiet gravitational environment. Neutron stars form when the cores of very massive stars collapse after a supernova explosion compressing matter beyond the structure of ordinary atoms. In these objects, protons and electrons are forced together under extreme pressure, forming neutrons and creating a state of matter governed by nuclear forces and quantum degeneracy. Neutron stars are extraordinarily dense compared to any other stable form of matter in the universe. A single teaspoon of neutron star material would contain mass comparable to a mountain, reflecting the extreme compression that occurs during their formation. Despite this density, neutron stars are stable due to neutron degeneracy pressure and strong nuclear interactions that resist further collapse. They exist as compact spheres only a few tens of kilometers across, yet contain mass greater than that of the Sun. In the long-term evolution of the galaxy, neutron stars become isolated objects. Most of them are born in energetic supernova events early in the galaxy's history, but as time passes and massive star formation ceases, no new neutron stars are created. The existing population continues to move through space along stable gravitational orbits, gradually becoming more separated from one another as the overall structure of the galaxy evolves and expands internally. Many neutron stars are initially observed as pulsars emitting beams of electromagnetic radiation from their magnetic poles. As they rotate, these beams sweep across space, producing regular pulses of detectable signals. However, over extremely long timescales, neutron stars gradually lose rotational energy. Their magnetic fields weaken, and their emission of radiation diminishes. Eventually, they transition from active pulsating objects into quiet, non-luminous remnants. The interior structure of a neutron star remains stable even as its external emissions fade. Beneath the crust, matter exists in exotic states where nuclei are crushed into dense nuclear material. The outer layers consist of a rigid crust of atomic nuclei embedded in a sea of degenerate electrons, while deeper regions contain increasingly dense neutron-rich matter. The exact structure of the deepest interior remains uncertain, with models suggesting possibilities ranging from superfluid neutron matter to more exotic phases involving quark components, but direct observational confirmation remains limited. As neutron stars age, they cool through the emission of neutrinos and thermal radiation. This cooling process is slow due to their dense structure, but over long periods their surface temperatures decrease significantly. Their once hot surfaces become cold and dark, reducing their visibility across the electromagnetic spectrum. Despite this cooling, their mass and gravitational influence remain unchanged, preserving their role as compact gravitational objects within the galaxy. The isolation of neutron stars becomes more pronounced as the galaxy evolves into a more diffuse environment. Without frequent stellar interactions or nearby energetic events, neutron stars drift through space largely undisturbed. Occasionally they may interact with other compact objects or pass through regions of sparse interstellar material, but such events become increasingly rare over time. In binary systems, neutron stars can still interact with companion objects if such systems remain gravitationally bound. In some cases, these interactions can lead to accretion of material-producing bursts of high-energy radiation. However, as the galaxy ages and stellar populations decline, the frequency of such systems decreases, reducing the occurrence of these energetic phenomena. Eventually, neutron stars become among the most stable and long-lived objects in the galaxy. They do not undergo significant internal change over extremely long timescales, and their evolution slows to near stasis once cooling is complete. Their presence marks the final remnants of massive stellar evolution, preserved in compact form long after the processes that created them have ceased. In the broader galactic context, neutron stars represent a transition point between active stellar processes and the final stages of matter evolution. They embody the extreme outcomes of gravitational collapse while persisting as stable, isolated objects in a universe where large-scale energy production is steadily diminishing. Their long-term survival highlights the durability of matter under extreme conditions, even as the surrounding environment becomes increasingly quiet and diffuse. Within the quiet galaxy where neutron stars drift as isolated remnants of ancient stellar collapse, The next inward region of cosmic evolution is defined by the dominance of black holes as the most enduring gravitational structures. Black holes form when extremely massive stars collapse beyond the neutron star stage, compressing matter into a region where gravity becomes so strong that not even light can escape. This boundary, known as the event horizon, marks the limit beyond which information cannot return to the surrounding universe. In the long-term structure of a galaxy, black holes persist as stable endpoints of gravitational collapse. They do not radiate light in the conventional sense, and they are detected only through their gravitational influence on nearby matter or through radiation emitted when material falls into them. Over time, as the galaxy's supply of gas and stars diminishes, fewer interactions occur that feed black holes with new material. Despite this, their masses remain locked within extremely compact regions of space. Supermassive black holes located at the centers of galaxies represent the largest of these objects. They contain masses ranging from millions to billions of times the mass of the Sun, and have grown over cosmic history through mergers and the gradual accumulation of surrounding matter. In earlier epochs, these black holes were often active, surrounded by bright accretion disks formed from infalling gas. In such states, they could outshine entire galaxies. However, as the universe ages and available matter decreases, these active phases become less frequent. Stellar mass black holes formed from individual massive stars are scattered throughout galaxies. These objects remain after the death of their progenitor stars and persist as compact gravitational sources. Over long periods, they may drift through the galaxy, occasionally interacting with other stars or compact objects. In dense environments such as stellar remnants clusters, interactions between black holes can occur, sometimes leading to mergers that release energy in the form of gravitational waves. As the galaxy evolves, black holes increasingly dominate the remaining bound mass in compact form. While stars fade and gas is depleted, black holes retain their mass and gravitational influence. They become the most significant contributors to the structure of the galaxy's central regions and sparse outer distributions. However, without sufficient surrounding material, their ability to grow through accretion becomes limited. Accretion, the process by which black holes gain mass from surrounding matter, depends on the presence of gas dust or stellar debris falling into their gravitational influence. In earlier stages of galactic evolution, this process can be highly energetic, producing luminous emissions from hot accretion disks. In the later stages, as material becomes scarce, accretion slows dramatically, and black holes enter long periods of inactivity. Mergers between black holes remain one of the few significant events that can still occur in this era. When two black holes orbit each other closely, they lose energy through the emission of gravitational waves, gradually spiraling inward until they merge into a single, more massive black hole. These events are rare but represent some of the most extreme gravitational interactions in the universe. Over time, even these interactions become less frequent as the population of black holes becomes more isolated. The interior structure of black holes remains hidden from external observation. According to current physical understanding, matter that crosses the event horizon is no longer accessible to external measurement. The central region, often described as a singularity in classical models, represents a breakdown in known physical descriptions where density and curvature become extreme. However, the true nature of this region remains uncertain, and quantum effects are expected to play a significant role in any complete description. Despite their invisibility, black holes define much of the large-scale gravitational structure of the late universe. They anchor the centers of galaxies and influence the orbits of surrounding remnants. Even as luminous matter fades, black holes continue to shape the dynamics of their environments through gravity alone. As time progresses, black holes become the last major repositories of concentrated mass in the universe. Stars' gas and even compact remnants like neutron stars and white dwarfs eventually either become isolated or are consumed. What remains is a landscape increasingly defined by these dark gravitational wells scattered across vast expanding regions of space. In this stage of cosmic evolution, the universe transitions from one dominated by luminous objects to one defined primarily by invisible mass. Black holes represent the final stable endpoints of gravitational collapse before even their long-term evolution begins to take over. They persist as silent structures shaping the last coherent gravitational systems in a universe gradually losing its energetic complexity. Within the universe now dominated by black holes and fading stellar remnants, the next inward region of cosmic evolution is defined by the gradual exhaustion of accretion processes, where even the most powerful gravitational objects begin to lose access to surrounding material. Accretion is the process by which black holes gain mass as gas dust and stellar debris fall into their gravitational influence, forming hot and energetic disks before crossing the event horizon. In earlier cosmic eras, this process can produce immense radiation, but in this late stage of the universe, the supply of matter becomes increasingly sparse. As galaxies age, most of their interstellar gas has already been consumed by star formation, or expelled through energetic feedback from earlier generations of stars and black hole activity. What remains is a diffuse low-density environment where matter is widely separated. In such conditions, the likelihood of material falling into a black hole decreases significantly. Without a steady inflow of matter, black holes enter long periods of quiescence, where they exist primarily as isolated gravitational objects with minimal external interaction. Stellar debris, once abundant in active galaxies, becomes rare. The remnants of disrupted stars or planetary systems may still exist, but they are scattered across vast regions of space. Occasionally, some of this material drifts close enough to a black hole to be captured, producing a brief episode of accretion activity. These events are increasingly rare and isolated, separated by immense periods of inactivity. The universe gradually shifts away from energetic processes toward long-term stability and decay. Even supermassive black holes at the centers of galaxies experience this decline. In earlier stages, these objects were often surrounded by dense accretion disks fed by inflowing gas, producing luminous, active galactic nuclei. Over time, as gas supplies diminish, these central engines shut down. The black holes remain, but their surrounding luminous structures fade, leaving behind dark, massive cores embedded in increasingly empty galactic centers. The structure of space around black holes becomes more stable in this era. Without frequent infalling matter, the environment around them is dominated primarily by gravitational influence, rather than energetic feedback. Orbits of nearby remnants such as white dwarfs, neutron stars and smaller black holes continue in stable trajectories, unless disturbed by rare close encounters. The dynamical evolution of these systems slows significantly as interaction rates decline. On larger scales, galaxy clusters continue to drift apart due to cosmic expansion, further isolating black holes within their respective gravitational regions. Each cluster becomes a closed system with limited internal evolution. Within these systems, black holes represent the most enduring sources of mass concentration, but even they are no longer actively growing. The universe becomes increasingly partitioned into isolated gravitational pockets containing dormant remnants. As accretion fades, the observable energy output of the universe declines sharply. The bright signals that once defined galaxies' stellar light supernova explosions and energetic emissions from accretion disks become rare or non-existent. The background radiation field continues to redshift and cool, gradually losing energy as space expands. The universe transitions toward a state where radiation is no longer a dominant feature of its structure. Black holes remain unaffected in their fundamental mass and gravitational properties, but their interaction with the surrounding environment becomes minimal. Without accretion, they no longer convert in falling matter into radiation. Instead, they persist as silent gravitational anchors shaping the motion of any remaining nearby objects without emitting detectable light of their own. In this stage, the universe is defined by inactivity on large scales. Energy-generating processes that once shaped cosmic structure have largely ceased. What remains is a network of isolated gravitational objects with black holes representing the most significant among them. Their role shifts from active growth to passive endurance, marking the end of most dynamic astrophysical processes. Over extremely long timescales, even the rare interactions that still feed black holes become negligible. The universe moves toward a state where accretion is effectively absent, and black holes exist in long periods of isolation. This marks a transition point in cosmic evolution, where the last major processes of matter exchange and energetic transformation fade into near silence. Within the universe, where black holes exist in long periods of inactivity, the next inward region of cosmic evolution is defined by the dark era of photon scarcity, a phase in which radiation becomes extremely rare, and the cosmos is dominated by low-energy, widely stretched photons that carry very little information or usable energy. In earlier epochs, radiation played a central role in shaping structure, from the intense light of stars to the energetic background of the young universe. In this late stage, radiation persists only as a faint and diffuse background gradually weakened by the continuous expansion of space. Photons, which are particles of light, lose energy as they travel through expanding space due to cosmological redshift. This process stretches their wavelength, reducing their frequency and energy over time. In the distant future, this effect becomes extreme, transforming once energetic radiation into extremely low-frequency signals that are difficult to detect and carry minimal physical influence. The universe becomes increasingly transparent, but also increasingly dark in terms of usable electromagnetic energy. The cosmic microwave background, once a strong remnant of the early universe, continues to cool and redshift. As it expands, its temperature drops steadily, and its photons become longer in wavelength. Over immense timescales, this background radiation blends into a nearly uniform low-energy field that permeates space, but contributes little to observable structure or energy exchange. It becomes a faint reminder of the universe's earlier hotter state. In this environment, black holes and stellar remnants exist in near isolation, with very little external radiation interacting with them. Without significant incoming photons or energetic particles, most astrophysical processes slow to near inactivity. The universe no longer supports widespread radiation-driven phenomena such as star formation, stellar heating, or active galactic nuclei. Instead, radiation exists primarily as a passive background feature. The scarcity of photons also affects the visibility of cosmic structures. In earlier epochs, light from stars and galaxies provided a rich and varied view of the cosmos. In the dark era, such sources are absent or extremely rare. The sky becomes dominated by faint infrared microwave, and eventually radio frequency signals that carry little detail. Observers, if present, would find the universe increasingly difficult to interpret through electromagnetic means alone. Despite this scarcity, radiation is never entirely absent. Black holes, even in isolation, emit extremely weak Hawking radiation due to quantum effects near their event horizons. However, in this era, such emissions are incredibly faint compared to earlier cosmic radiation sources. The energy output from these processes is negligible on macroscopic scales, contributing only slowly to the long-term evolution of black holes. The background temperature of the universe continues to decline as expansion stretches space further. This cooling affects all forms of radiation, uniformly gradually reducing the energy density of the cosmos. Matter and radiation become increasingly decoupled, with interactions between them becoming rare events. The universe transitions toward a state where radiation no longer plays an active role in shaping structure. In this photon-scarce environment, the distinction between different regions of space becomes less defined. Without strong radiation fields, there are fewer observable markers of cosmic structure. Galaxies, once visible as bright and distinct systems, are no longer detectable through conventional means. Only gravitational effects remain as a way to infer the presence of mass and structure. The long-term fate of radiation is governed by both expansion and the lack of new sources. With no new stars forming and no energetic astrophysical events occurring, the universe has no significant mechanism to generate fresh high-energy photons. Existing radiation simply continues to stretch and weaken over time, gradually losing its ability to influence matter or be detected. As photon density decreases, the universe approaches a state where radiation is effectively negligible in terms of energy contribution. Matter and gravity dominate the remaining physical processes, while radiation becomes a faint background residue of earlier cosmic epochs. This transition marks a fundamental shift in the universe's energy balance, moving away from radiation-dominated dynamics toward matter and gravity-dominated persistence. Over immense timescales, even this faint background continues to fade. The universe becomes quieter in electromagnetic terms, with fewer and fewer signals capable of carrying information across space. The dark era of photon scarcity represents a long, stable phase in which the universe is still physically present, but increasingly devoid of energetic interactions mediated by light. Within the universe, now dominated by extremely weak background radiation and isolated gravitational structures, the next inward region of cosmic evolution is defined by quantum vacuum stability, a phase in which matter exists in its lowest accessible energy configurations and large-scale processes have largely ceased. The vacuum is not empty space in a simple sense, but a physical state governed by quantum fields that permeate all of space. Even in the absence of particles, these fields continue to fluctuate at microscopic scales, producing transient variations in energy and field strength. In this late cosmic era, most matter has already settled into stable or nearly stable forms. Stars have long since ceased forming, and the remaining stellar remnants have cooled significantly. Black holes persist as the dominant massive objects, while diffuse particles and radiation exist only in extremely low densities. The universe as a whole approaches a state where changes occur only through rare and slow quantum processes, rather than through large-scale astrophysical activity. The quantum vacuum itself represents the lowest energy state of physical fields, but it is not completely static. Even in this state, temporary fluctuations arise due to the uncertainty principle, a fundamental feature of quantum mechanics that allows energy and time to vary within strict limits over extremely short durations. These fluctuations do not produce lasting structures in ordinary conditions, but they remain a persistent feature of the underlying physical framework. As the universe expands and cools, these quantum fluctuations become more isolated and less likely to produce observable effects. The separation between particles increases and interactions between them become extremely rare. Matter becomes so diffuse that large-scale chemical or thermal processes effectively cease. What remains is a universe where the dominant activity occurs at the smallest scales of physical law, Particles that remain in this environment are generally stable forms of matter, such as electrons, protons, and long-lived atomic nuclei. Over extremely long timescales, however, even these particles may be subject to rare decay processes, depending on whether certain theoretical predictions such as proton decay are realized in nature. These processes, if they occur, would gradually transform matter into lighter particles, and radiation further simplifying the structure of the universe. Black holes continue to exist during this phase, but their interaction with the surrounding environment becomes increasingly limited. Without surrounding matter to accrete, they lose mass only through extremely slow quantum processes such as Hawking radiation. This emission is incredibly weak, and becomes more significant only over timescales far exceeding those of earlier cosmic evolution. The evaporation of black holes represents one of the final dynamic processes in the universe. The vacuum state surrounding these objects remains largely unchanged on macroscopic scales. Space itself continues to expand, but local regions are dominated by gravitationally bound systems or isolated particles. The absence of significant radiation or matter flow means that energy exchange between regions is minimal. The universe becomes increasingly uniform in its low-energy configuration. In this phase, the distinction between structure and emptiness begins to blur. Without stars, galaxies, or energetic processes, space appears uniform, except for the presence of isolated remnants and quantum fluctuations. The physical laws remain fully active, but their effects manifest only at microscopic or extremely long temporal scales. Quantum processes such as particle tunneling and vacuum fluctuations continue to operate, but they do not lead to large-scale structure formation under normal conditions. The universe remains stable in a statistical sense with no dominant direction of evolution, except the slow progression toward lower energy states. This stability defines the vacuum-dominated era as one of minimal macroscopic change. Over extremely long timescales, the balance between matter radiation and vacuum energy becomes increasingly simple. Most energetic processes have already ceased leaving behind a universe where only rare and gradual transformations occur. The vacuum state persists as the underlying framework for all remaining phenomena supporting the final remnants of matter and gravitational structure. In this stage of cosmic evolution, the universe is no longer shaped by visible events, but by the persistent underlying structure of quantum fields and gravitational remnants. Change becomes increasingly subtle, driven not by energetic interactions, but by the slow unfolding of fundamental physical processes at the deepest levels of reality. Within the universe where macroscopic activity has largely faded, the next inward region of cosmic evolution is defined by black hole evaporation onset a phase in which the most massive remaining objects begin to lose mass through extremely slow quantum processes. Black holes once formed from the collapse of massive stars or grown at the centers of galaxies are traditionally understood as regions from which nothing can escape. However, quantum field effects near the event horizon introduce a gradual emission of particles known as Hawking radiation, which allows black holes to lose energy over immense timescales. Hawking radiation arises from quantum fluctuations in the vacuum near the boundary of a black hole. In simplified terms, particle-antiparticle pairs can form briefly, due to quantum uncertainty, and under extreme gravitational conditions one of these particles may escape while the other falls into the black hole. The net effect when viewed over extremely long periods is a slow reduction in the black hole's mass. This process is extraordinarily weak for large black holes, making it effectively negligible on short cosmic timescales. In this phase of the universe, most black holes are extremely isolated. They no longer receive significant infalling matter because earlier stages of cosmic evolution have already depleted surrounding gas dust and stellar remnants. Without accretion, Hawking radiation becomes the primary mechanism governing their long-term evolution. This marks a fundamental shift from growth and interaction to gradual decay. Supermassive black holes at the centers of former galaxies are among the most stable structures at this stage. Their immense mass makes their evaporation timescales extraordinarily long, far exceeding the current age of the universe by many orders of magnitude. Stellar mass black holes, though smaller, also evaporate extremely slowly, with lifetimes that remain vastly longer than any previously active astrophysical process. As black holes emit Hawking radiation, they gradually lose mass and energy. This emission is not uniform in its composition. It consists of a spectrum of particles including photons, and in later stages of evaporation, increasingly massive particle species depending on the energy scale of the black hole's temperature. However, for most of their existence in this era, the radiation is extremely low energy and difficult to distinguish from the background environment. The temperature of a black hole is inversely related to its mass. Larger black holes are colder and emit less radiation, while smaller ones are slightly warmer and evaporate more quickly. In this late universe, even the smallest remaining black holes are still massive by everyday standards, meaning their temperatures remain extremely low and their radiation extremely weak. As a result, evaporation proceeds at a nearly imperceptible rate. The surrounding universe provides little external influence on this process. With matter and radiation already extremely sparse, black holes evolve in near isolation. Their evaporation is not driven by external interactions, but by internal quantum properties of space-time itself. This makes black hole evaporation one of the most fundamental and isolated processes in the late universe. As evaporation continues, black holes gradually shrink. Their event horizons reduce in size and their gravitational influence weakens correspondingly. However, this reduction occurs over timescales so vast that the process remains effectively static over any ordinary observational period. The universe at this stage changes only through cumulative effects across immense durations. The energy released by Hawking radiation slowly returns to the surrounding space, contributing to an extremely faint background of particles and radiation. This background is negligible compared to earlier cosmic radiation fields, and does not significantly alter the structure of the universe. Instead, it represents a final redistribution of mass energy from compact objects back into a diffuse state. Eventually, as black holes continue to evaporate, their final stages become more dynamic in relative terms. As their mass decreases, their temperature increases, causing them to emit radiation more rapidly. However, this final phase occurs only after extremely long periods and represents a late transition in their evolution rather than an immediate process. In the broader cosmic context, black hole evaporation marks one of the last active physical processes capable of significantly altering the distribution of mass energy in the universe. It represents a transition from stable remnants to gradual dissipation, moving the universe closer to a state of extreme low-energy equilibrium. Within the universe, where black holes are slowly evaporating and all large-scale astrophysical activity has already ceased, the next inward region of cosmic evolution is defined by particle decomposition uncertainty, a phase in which the long-term stability of matter itself becomes a central feature of cosmic time. At this stage, the universe contains only isolated remnants of earlier structures, including black holes in their final stages, extremely diffuse radiation, and sparse, long-lived particles. The behavior of matter is no longer governed by energetic astrophysical processes, but by the deepest and least frequently observed principles of particle physics. Protons, electrons, and other stable particles form the remaining scaffolding of physical existence in this era. In standard physical understanding, electrons are stable and do not decay under known conditions. Protons are also considered stable in the standard model of particle physics, yet some extended theoretical frameworks allow for the possibility of proton decay over extremely long timescales. If such processes occur, they would transform protons into lighter particles such as positrons, neutrinos, and photons, gradually dissolving atomic nuclei and simplifying matter into more fundamental components. The uncertainty surrounding proton stability defines a major boundary in the long-term evolution of the universe. If protons are absolutely stable, matter can persist indefinitely in atomic form, even as all energetic processes fade. If proton decay is possible, then even atomic structure itself becomes temporary, eventually breaking down into a diffuse mixture of leptons and radiation. In either case, the universe evolves toward increased simplicity, but the endpoint depends on physical laws that are still not fully confirmed. As black holes continue to evaporate, the universe becomes increasingly dominated by low-energy particles produced by quantum processes. These particles spread across vast regions of space, interacting only rarely due to extreme dilution. The density of matter and radiation becomes so low that collisions and interactions between particles become statistically rare events, separated by immense intervals of time and distance. In this environment, atomic nuclei, if they remain stable, drift through space without significant interaction. They may persist as isolated hydrogen atoms, or as heavier nuclei that have survived earlier stages of stellar evolution. Without energetic radiation fields or gravitational collapse mechanisms, these atoms remain largely unchanged over long periods, representing the final stable configurations of baryonic matter. The concept of decomposition in this phase does not imply sudden destruction, but extremely slow and rare transitions between states. Quantum tunneling processes, if applicable, may allow particles to transition into different forms under highly improbable conditions. However, these events occur on timescales so vast that they define the structure of cosmic time itself rather than any observable sequence of events. The universe at this stage is extremely uniform in its physical behavior. Without stars, galaxies, or black holes exerting significant influence, matter exists in a state of near total isolation. Each particle or atom becomes effectively independent, with its evolution governed primarily by intrinsic stability rather than external forces. The large-scale structure of the universe becomes irrelevant compared to these microscopic properties. Radiation produced by earlier black hole evaporation continues to spread, and redshift contributing to a faint and uniform background. This radiation carries little energy and interacts weakly with matter, reinforcing the isolation of particles. Over time, even this background becomes more diffuse, blending into an extremely low-energy state that contributes minimally to physical processes. The uncertainty surrounding fundamental particle stability introduces the possibility of multiple long-term outcomes for the universe. In one scenario, stable matter persists indefinitely in a cold, dilute state, dominated by long-lived atoms and particles. In another scenario, gradual decay processes eventually reduce all matter to radiation and neutrinos, leaving no bound structures. Both outcomes represent extensions of known physics, but their ultimate realization remains uncertain within current theoretical frameworks. In either case, this phase represents a universe in which change is governed by extremely rare events rather than continuous processes. The evolution of matter is no longer driven by astrophysical dynamics, but by the statistical behavior of quantum fields over vast timescales. The universe becomes a system where stability and decay coexist at the limits of physical possibility. As time progresses further, even the distinction between stable and unstable matter becomes less significant, as the frequency of all interactions diminishes. The universe approaches a regime where only the most fundamental properties of particles remain relevant and all large-scale structures have already dissolved into their simplest components. Within the universe, now reduced to its most isolated particles, fading radiation, and the final remnants of evaporating black holes, the next inward region of cosmic evolution is defined by the final dilution of everything, a phase in which energy, matter, and structure approach a state of extreme dispersion across expanding space. At this stage, the universe no longer contains organized systems such as galaxies, stars, or stable accretin structures. Instead, it consists of widely separated particles and low-energy radiation distributed across an ever-growing volume. As cosmic expansion continues indefinitely, the distance between remaining particles increases steadily. Even though local physics remains unchanged, the probability of interaction between any two particles becomes extraordinarily low. Matter is no longer clustered into recognizable forms, but exists as isolated points embedded in an almost perfectly empty spatial background. The concept of structure loses its meaning on large scales, replaced by a statistical description of rare independent events. Radiation from earlier black hole evaporation and other late-stage processes continues to redshift and lose energy. Photons that once carried significant information about cosmic structures now stretch to extremely long wavelengths, reducing their ability to interact with matter. This radiation becomes increasingly uniform and indistinguishable from a background field, contributing little to the overall dynamics of the universe. If proton decay or similar processes occur in nature, then even atomic nuclei eventually break down into lighter particles over immense timescales. In such a scenario, the universe gradually transitions from a matter-dominated state to one composed primarily of leptons, neutrinos, and low-energy photons. If protons remain stable, then isolated atoms may persist, but even these structures drift apart without forming larger systems. Black holes, once the most persistent structures in the universe, have by this stage already completed most of their evaporation process. The final stages of black hole evaporation produce bursts of radiation as their mass approaches zero, but these events are separated by vast periods of cosmic time and occur in extreme isolation. After these final emissions, no further black holes remain, removing the last gravitational structures capable of significantly shaping their surroundings. Without stars or black holes, gravity still exists but has little material to act upon. Large-scale gravitational structures have already dispersed, and only minimal local interactions persist between isolated remnants. The universe is no longer organized into systems, but exists as a diffuse field of independent particles moving through expanding space. Thermodynamic equilibrium becomes the dominant concept in this phase. Energy is distributed so evenly across space that no usable gradients remain to drive physical processes. Temperature differences diminish toward near uniformity, and entropy approaches a maximum state. In this condition, the universe no longer supports processes that extract work or sustain complexity. The passage of time continues, but it no longer produces meaningful structural change. Instead, time marks the increasing separation and dilution of existing particles. Events become so rare that the universe is defined more by the absence of interactions than by their presence. Each particle exists in a long-term state of isolation, with minimal probability of encountering anything else. In this final dilution phase, the universe reaches a state often described in physical terms as heat death, where all available energy has been evenly distributed and no further thermodynamic processes can occur on a large scale. This does not imply disappearance of the universe, but rather the absence of gradient structure and activity that would allow change to be observed in any meaningful way. What remains is a vast expanding and nearly empty space-time filled with extremely low-energy particles and radiation. All earlier cosmic structures, galaxies, stars, planetary systems, black holes, have either decayed, evaporated, or dispersed beyond recognition. The universe persists, but only in its most minimal physical form, defined by uniformity isolation and the near total absence of interaction.